Sharing my screen just so that I can see most students. Okay, we're getting started. It's 9:04. So those that came in, and I'm not just talking to one person because I've been clicking admit a lot after 9 o'clock. Let's remember, we need to be here at 9 o'clock. You can try to get in early, but like with anything else, if this was regular school face-to-face, you would be here when the bell rings. So let's try to get here a little bit earlier. Outside of that, I'm not picking on anybody. It's multiple people. I just want to focus on the work now. Biggest question of the day. Let me stop the share just for a minute so we can digest what we were just looking at. Biggest question today is probably about grades. More people coming in. All right. The grades, have the test been graded? Answer is yes. Are the grades in? Answer is no. Okay, so I must stop admitting people at some point. Let me make sure this is the right person. Yes, okay. Okay, there's a single grade for you right now in Canvas. The overall average, let me pull it up and see what it was. It was 76% was the overall average. I was happy with the average that I was seeing because I had a lot of grades that were very impressive. Overall, I'm pretty proud of what was done. The FRQs, most of them were very thoughtful. Some of them introduced their ideas with a physics fact and went on from there. Very, very nice jobs. Now, the reason I say you can't trust the grade in Canvas is because we're going to divide the grade and it won't be an equal like, oh, I got a 80 on it, so now I have two 80s. Well, you may have gotten 100 on one chunk and you might have gotten a 60 on another chunk, and now you have 100 and a 60 in Hack. So don't trust it till you see it in Hack. I hope to have it in Hack before midnight tonight. Maybe well before that, maybe after that, but my desire is before I go to sleep tonight, it's in Hack. Will there be a curve? Quite possibly on one of the tests. We will find out, or we will decide today during third period when all the AP1 teachers get together and we measure our scores against one another and see, was there a disproportionate lower grade on one test compared to the other beyond what we would anticipate. So far, the scores in our class look very well. They're strong. And when I say the overall score was a 76, that's across, I have 98 students and 40 of them are in this class. So y'all aren't half of them, y'all are less than half. So there are other classes contending in that score. Now, looking at individual scores, we're gonna review the test next class, probably. That means we're gonna go through all of the test questions. That is the best place for you to get the information to figure out what went wrong. I understand though that 98 students want to sit down and find out what multiple choice did I miss, what this, what that. That becomes extremely challenging. And if you attend tutorials, I'll definitely pull something up and look at it with you. Through email, it gets overwhelming, the number of requests. And then I start kind of pushing back and saying, make sure you pay attention during the review. I reviewed every single question with you, okay? So let's just get that kind of out of the way. Can you trust Canvas, the grade in Canvas? A little bit, but not much. All right, so now let me see what's in the chat. Oh no, don't worry about anything about apologies, none at all. There were multiple people coming in after 9, so don't worry about it. Just let's target things, you know, try to be here like it was face-to-face, try to be here at like 10 till, and I open up usually around 5 till, just depending. Will there be another test in this 9-week period? That's a good question. We haven't fully planned out this next unit. This is 2 tests, 2 major grades, which is the minimum. There will be retests. Will there be a test within forces? I haven't looked that far forward because we're just starting the unit and we're still kind of cleaning up and finishing the last unit. As soon as I have those dates, number 1, I'll tell you. Number 2, I'll put it in Canvas. It'll be in our calendar. And also I try to populate Hack ahead of time so you have a good idea. So as soon as I know that it's planned and for sure a certain day, you will certainly know. That's a good question though. Okay, now that we've gotten that out of the way, grades, we've taken a breath. I want you to monitor when your grade comes in, and I want you to ask, pretend like I'm just talking to you. So I'm not talking to anybody else. How is this class going? Okay, are we getting the work done? Are we understanding the work? Are we reaching out for help when we need it? And then how is the performance showing on the assessments? I need you to ask yourself those questions, because starting Friday, I think for 1 week, the ability to change classes and switch out of AP1 is available to you. I don't want anybody miserable. I don't want anybody suffering, but the grade you earn is the grade that you have once it hits HACC, once we get through retest. I just want you to be aware that there's not some sort of magic AP fairy that comes around and turns your, I'll be ridiculous so you know I'm not talking about anybody in particular, the 7% you have in this class won't become a 77%. Now, no one has a 7%, so I'm not talking about anybody in particular, but monitor your grades, ask yourself, how's this class going? And are you putting in the work that you need to be successful? So I want to make sure I'm having that conversation with 40 people right now, and you're taking it to heart, okay? If you decide that, that you need to talk to me about it, absolutely, email me. We will set something up. We can talk in Zoom. We can talk through email if we want to make the decision together. But you guys are young adults, and you need to be thinking about stuff like this. Now, that's out of the way. That's 10 minutes of class wasted on grades. So let's move on to actual forces. So I'm going to share this screen again. We don't need to unmute because I don't want to spend a lot of time on this. I just want to get some ideas out of the way. So agree, thumbs up. Disagree, thumbs down. So we're going to go through these statements. It tells us that Miss Lee's students share their ideas about force and motion. Here are some ideas they came up with. We want to know the ones that they agree with. This is agree, this is disagree, okay? If there is motion, then a force is acting. Do we agree or disagree? Okay, a lot of people agree. Now, let me ask, you can put them down. So I'm an astronaut, not really, but let's say I was, and I threw a baseball out into space. Would we agree that it's going to continue going on pretty much forever? Even after I go home and I land at Kennedy Space Center and now I'm retired and I'm hanging out at home, baseball's still moving, right? So wouldn't that be motion with no force currently acting on it? So A, not the best answer. But don't get me wrong, don't get too discouraged because we haven't talked about forces until now, so you're not really supposed to know this. We're just kind of getting some misconceptions going. If there is no motion, then there are no forces acting. Agree, disagree? So now you're getting the trend. Absolutely, we're going to disagree with this. Isn't gravity acting on all of us right now? But are we moving? Or me, I'm not moving. Some of y'all are kind of moving around a little bit. So you can have forces acting and have no motion. I can push on the side of the school on the brick wall and apply a force as much as I can do. That brick wall is not going to move. Okay. There cannot be a force without motion. There cannot be a force without motion. Agree, disagree? Right. We're still disagreeing because just like me pushing on that brick wall, nothing is going to move that brick wall if it's just me pushing on it. So just because you have a force doesn't mean you're going to have a motion. Objects can continue moving in a straight line without applying a force. If we were listening, we know from A, this should be good because I can put something in motion and it keeps moving and there's no more forces acting on it. All right, when an object is moving, there's always a force in the direction of its motion. Disagree, because there may be no forces at all. Moving objects stop when the force is used up. Agree or disagree? Disagree, just like the baseball in space. Forces act on objects at rest. Do forces act on objects at rest? Absolutely. If I go out there and kick the soccer ball that's sitting in the grass outside, that's an object at rest, and my foot kicking it would be a force. The stronger the force, the faster an object moves. It's a trick question. So my immediate downs were right. You don't need a force to move fast. We will see an imbalance of forces creates an acceleration, but you don't need a force or a strong force to move fast. Let me see. Constant speed results from constant force. Constant speed comes from constant force. So we're going to disagree here. We're going to learn that constant speed comes from a balance of forces. If forces are balanced, we will have a constant velocity. A force is necessary in order to change the direction of motion. a force is necessary to change the direction of motion. This is absolutely right. If that baseball in space, in order for us to change its motion, we're going to have to apply a force that gives it an acceleration in the opposite direction, slowing it down, changing its direction. All right, two more. I know this is getting boring for me, so it must be for you guys. Forces make things go. Losing energy makes them stop. Yeah, it's down. And then forces can be transferred from one object to another during motion. Forces can be transferred down. Energy can be transferred, forces, no. Transfer the forces. All right, let's see. Somebody's coming in now. Okay, come on in. Let's stop the share. Okay, so those are a lot of statements. They're posted in Canvas. I believe there's probably descriptions to go along with it, so you can kind of go through each one. It's easy to take our assumptions of the world around us and apply it and say, well, obviously there's, if something's moving, there's a force. Well, not necessarily. That's what we're going to be learning today. We're going to go through Newton's first, second, and third laws. We'll define forces. We'll define each of the three laws. Then there's like a small packet that kind of takes us through forces. I'll take you through page 1. And as long as we keep a good pace, then we should be able to get that far today. You will finish the packet for class on today's Wednesday, for Friday. And when we come to school on Friday, we'll open the class and say, what questions did you have? What were you not able to finish? All right, so let's go, and I'm going to share my screen on this side so that we can write stuff. Okay, so if I'm writing, you're writing. I can see you guys, so I hope you can see me as well. I'll talk through these a bit. I just have to get set up for actually writing on my pad here. So the first thing I want to do is I just want to define a force. And I can't write on a pencil on the screen, so let me get a stylus out. All right, so a force. Drawing. All right, so write along with me or read along with me and write it later, because I'll post this Zoom class by end of day sometime. But we're going to say a force is a push or a pull. All right, a push or a pull. It is a vector. And if we remember a vector, that means that it has a magnitude and a direction. We're going to push with a certain amount of force, and it's going to be pushed forward or it can be pulled, but it'll be directional. It is a vector. All right, so examples. We have contact forces. This means we're actually in contact. Should be kind of obvious, a little bit obvious. These include friction, tension, normal force, thrust, spring, and then just a catch-all of applied. Okay, while you write those down, I'm going to talk through them a little bit. Friction force opposes movement. We know usually friction is what slows something down. So friction force is always in the opposite direction of movement. Don't worry about like writing everything I say. I just want you to hear this and start digesting it. Believe me, you'll have plenty of time to like overanalyze all of this stuff. Tension comes from ropes, chains, anything you would hang from. If you're hanging from a rope or a chain, that's tension force. Normal force is a surface force. So right now we're all sitting in a chair, it looks like, for the most part. So the force that the chair is applying to our backside is normal force. If we stand up, the floor or the carpet or the concrete outside, whatever we're standing on, applies a normal force. If we jump up in the air, we're not touching anything, no normal force. All right, thrust comes from engines. In an airplane, pushing you forward, right? In a car, but engines provide thrust, which propel things forward. Spring force can either push or pull, depending on if the spring from equilibrium is stretched or compressed. And then applied force it's kind of a catch-all. When we can say any of these we can say any force that we put onto something is an applied force, then we can be more specific with the ones I listed, Or if we are unable to, we could just have a catch-all of, hey, there was an applied force. Don't know what it was, but it was an applied force. So those are contact forces. We also have long range. So let me write long range. These would include, so we also call these field forces, but long range is a little bit easier to understand. Gravitational. So even if we jump up, gravity's still pulling us down, right? We don't have to touch something to experience gravity. So we have gravitational. We have electromagnetic. And we have magnetic. So regular magnets like on your refrigerator, you know, as you get close to the refrigerator, you can let go of it and they suck to it. Electromagnetic, like what you would use with, if they're picking up cars with cranes, they apply electrical current, the magnet starts to work, pick something up, take away the electrical current, magnet no longer is energized, so it drops whatever it was holding. And of course, gravity is pretty obvious because we've all experienced gravity, at least we're experiencing it right now. Now, weight, your weight is a force. We can say that weight, W, is equal to your mass times acceleration. Okay. We can also call this the force of gravity is equal to your mass times acceleration. Now, this is a rhetorical question. I don't intend anybody to answer it, but where does the acceleration come from? From your weight. Well, let's consider it. I think everybody but like 6 people are like, I know what this is. But for the 6 people that don't know, what if you went to the moon? Wouldn't you weigh less? But your mass would be the same. I'm not skinnier on the moon. I'm not fatter on Mars, right? My mass is constant. So the acceleration must be different, because if I go to the moon, according to the lunar landing, videos that may have been faked, I don't know. I'm just kidding. They weren't faked. I don't believe that. But on the lunar videos, they're bouncing around, right? Like they weigh very little because the acceleration is different. So where does the acceleration come from? Gravity. So in this case, the acceleration for weight, acceleration is gravity. Okay. And it's equal to 10 meters per second squared. So if we described the force of gravity, we could call it Fg. We could call it W, because weight, force of gravity. We could also call it mg, because it's the mass times gravity. So W is equal to Fg is equal to mg. When we start doing free body diagrams, any one of those 3 are equivalent. They're all the same. So if someone says, hey, what's weight, or why'd you put W on that free body diagram? I put Fg. They're the same thing. Weight is force times gravity. Force times gravity is mass times acceleration. Acceleration in this case is from gravity, so G. All right, so if we've got that, I'm going to clear this part of my screen and let's talk about Newton's first law. I'll give you a second just in case you're behind. You take a picture of it with your camera phone, whatever you need to do, and I'll clear this. Did Miss Hastings find you? No. You haven't seen Shelby today at all? She came here looking for you before class started. All right, you've had time to take a picture of this or get caught up whichever way. I'm going to clear this. If not, if for some reason I'm deleting this way too early, don't forget this is all recorded. You'll be able to get the recording sometime later today. It's in the Zoom links within Canvas, so it's all there. So let's talk about Newton's first law. Ooh, not shapes, drawing. All right, Newton. Usually this is where I have the bad joke of, I'm not talking about the fig Newtons, the fake cookies. Those are pretty nasty. It's a terrible joke. Probably doesn't play well over Zoom, so we'll just avoid that altogether. So let's say Newton's first law. Okay, this is the only one that really has a name to it, and it's the law of inertia. Now, what is inertia? I'm so glad y'all asked. feel like I'm talking to myself today. Tendency to resist change in motion. How do you spell tendency? Oh, there we go. Okay. Newton's first law, law of inertia. What is inertia? Tendency to resist change in motion. Think about you when your alarm goes off. You don't want to get up. Think about you when you're hanging out with your friends and it's time to go home. You don't want to go home. Think about a freight train that's driving down the tracks, right? It doesn't want to stop. That's why it's so difficult to get them going, so difficult to stop them. Tendency to resist changes. If we have an increase of mass, that equals an increase in inertia. It's a lot easier to push a small car than a big heavy truck pulling a trailer, right? So in a lot of cases, we're going to say mass and inertia act in the same way. I don't want to say they're the exact same thing, but just short of saying they're the same thing, they're kind of the same thing, okay? I don't say I have a lot of inertia, I have a lot of mass, but they act in the same way, okay? I know it give me a complex. I'd go on a diet, then I'd find that there's donuts in the workroom today. I've already eaten 2, started to feel gluttonous. It's really bad. All right, so I think most of us have heard of this law. I'm not going to write it all the way out because we're pretty familiar with it. But if I gave a big fancy definition to it, it would sound something like this. Every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied. Or we can say it a little bit differently. Every object in a state of uniform motion tends to remain in that state of motion unless acted upon by an unbalanced outside force. So objects in motion want to stay in motion. Objects at rest want to stay at rest unless acted upon by an unbalanced force. Okay, so I said 3 times, so it'd be a little bit more familiar to you. I hope that it's kind of sinking in. Some of that should be familiar. So you want to stay at rest or you want to stay at motion unless there's an unbalanced force, because an unbalanced force will give you acceleration, either in the same direction or an opposite. Okay, so what are some examples of balanced and unbalanced forces? Okay, here's my calculator. If I push on it with my right hand and I push on it with my left hand and I balance those forces, calculator's not moving, right? I'm actually pushing pretty hard. It's starting to wiggle. Now, if I push less with my left hand and more with my right, it goes this way. If why am I not moving right now? Why am I not sinking? I've got gravity pulling me down. Well, I have a balanced force of the chair pushing up. So unbalanced forces and balanced forces, if you have a constant velocity, even if the velocity is 0, if you have a constant velocity, you have balanced forces. It could be no forces at all because 0 plus, with an opposing 0, those are balanced. But for me not to be moving in any direction right now, that means that all the forces acting on me are balanced. If I start to accelerate, then I have an imbalance of forces. If I reach a velocity and then maintain that velocity, I've balanced the forces. I'll give you one more example. If you're driving in a car and you're at a stoplight, you're not moving, constant velocity of 0. Your forces are balanced. Once the red light turns green and you push down the gas pedal, you start to accelerate. The thrust of the engine is more than the drag on the car. Therefore, you are accelerating. But once you get up to 60 miles an hour, you set your cruise control for 60 miles an hour, you are now balancing the thrust to any drag on the car or any friction on the car. Your forces are balanced and you will maintain a velocity that is constant. So it's balanced when you're stopped, it's balanced when you're going to constant velocity, whatever that velocity is. We okay with this so far? I'm not blowing anybody's mind yet, right? It should be kind of a little bit more than basic, but not by much. So if we've got that, let's move on to the second law. Okay, so I'll just write below this. So drawing, let's just put second law. All right, half or more of our problems will come from the second law because the second law actually has an equation. Here we're going to say the net force acting on the object will cause it to accelerate. The net force acting on the object will cause it to accelerate. What does that mean? If I apply 10 newtons of force, and we measure force in newtons, if I apply 10 newtons of force going to the right and only 8 going to the left, the net force would be 2 to the right, and that's where the acceleration would be. You add up all the forces going one way, and you add up all the forces going the opposite way, and the sum of those forces, you subtract the opposing forces, whatever's left over in that direction will be the direction of your acceleration. So the net force acting on an object will cause it to accelerate. Our formula, let's see if I can do a summation sign. All right, so that's gonna be the prettiest summation sign you ever see from me. After that, it's gonna look like a big ugly E, but that's my summation. So the summation of forces is equal to the mass times the acceleration. The direction of that force is the same direction of that acceleration. So I put an arrow over force to say that the direction from the sum of forces will be the same direction that we get from the acceleration. And since we're introducing mass, mass is measured in kilograms. So we know that velocity was meters per second, acceleration is meters per second square. Let's see, what else did we do? Time was in seconds, distance was in meters. Now mass is in kilograms. I mentioned that for force is in newtons, and we'll abbreviate that just with an N. While we're doing these problems, we're also always going to draw a free body diagram. Don't worry, we'll see that in a little while. But if you see something that says FBD, that means free body diagram. Now, most of mine I draw as squares. Some people use circles. I think on the test they use a circle, but when we get started, I'm going to start with a square, a box, a rectangle, because it's easier to demonstrate the forces coming off of a box than a very tiny circle. Okay, so for the learning process, we'll be doing that. Okay, so we did Newton's first law. When you're in bed, you want to stay in bed, all right? When you're having fun driving down the road, you want to keep driving down the road. That's Newton's first law. Unless you have an unbalanced force, that's the parent telling you come on home, right? Newton's second law, sum of forces is mass times acceleration, the only equation of the day. The fun part of that equation is when we start doing the sums of forces, if you were in the classroom, you'll see I can make a 6 foot long, literally 6 foot long equation from the sum of forces, but it just comes from add up all the forces and you can set that equal to mass times acceleration. Are we okay with Newton's first 2 laws? All right, we're awake, we're okay, we're dying. Let's get some feedback. Oh, I got an angle, wow, okay. I got somebody who's like, okay. All right, today's a bad day for physics because it's not fun. We're just talking about terminology. We're getting some ideas down. We're just getting started. Forces becomes fun. We just have to get the foundation so we understand what we're talking about. All right, let me clear this off. Again, it's going to be in the Zoom recording, so you have access to it. I don't want that one. I want this one. All right, let's box this up. Let's get rid of that. Okay, Newton's third law, the last one, the one that only makes a little bit of sense, okay? So let's say Newton's third law. These are action-reaction force pairs. Okay, now, did I indicate somewhere that one of those words is more important than the others? All right, action-reaction force pairs, not triplets, not quadruplets, force pairs. What does this mean? Okay, let's see if I've got words for this. When you push on something, it always pushes back, the reaction force. It recurs in pairs. So if I push on this wall very lightly, it pushes back on me very lightly, right? If I hit this wall lightly, I'll hit the board so it won't be as loud. Hit the wall, let's see, let me move this down. I'm actually hitting the wall. Shelby's gonna be like, what is he doing? All right, I hit the wall, it hit me back. Now, if I hit the wall really hard, is it gonna hurt? Absolutely, it's gonna hurt. If I hit it softly, will it hurt? No, because the wall is gonna hit me as hard as I hit it. Now, did the desk get involved? I'm sitting at a desk. I don't know if you can see it. I'm sitting at a desk, okay? Did the desk get involved with me hitting the wall? No, because it's a pair, it's two, okay? So for Newton's third law, there's only two things. So when you see a question that talks about A acted on B, so then what happened? The only solution is B acts back on A. You can't reach out and say, well, his friend showed up and did something. Let me come in. There's something put in here. Let me see what this is. For the third law, would jumping also count as an opposite reaction? Okay, we can be more specific with that. So someone asked me, for the third law, would jumping also count as an opposite reaction? If we push up off the earth with our feet so that we can jump, what would the reaction be? Of course, it's a question I just want you to put in your head. I'm pushing off of the earth so that I can jump up into the air. So if I'm the A, the earth is the B. If I push on the earth then would have to push up on me. Okay? Now, what about this? We're all sitting down. You're in your house. I'm at school. The earth is pulling down on us. It's called gravity, right? What's the reaction? I want someone to unmute and tell me, what's the reaction? The earth is pulling on me. It's pulling on you. The earth is pulling on us. What is the reaction?
You're pushing against gravity.
Well, I'm not pushing against gravity. The gravity's pulling down on me. So what am I doing back?
On Earth.
I'm pulling up on the earth. Right now, that's happening according to Newton's third law. If the earth is pulling down on me, I'm pulling up on the earth. It's really weird to hear for the first time. I get it. It's weird when I heard it the first time. Sometimes weird to say it, but it's the case. There's always, and it's just a pair. I can't say, well, anything other than just that A and B. I can't include anything else because it's a pair. I circled it, I underlined it like 3 times, and I put 2 arrows going towards it. It's a pair. All right, let's see what else we can say. We have action-reaction pairs. When you push something, that's the action force. So when you push something, it's funny is I can hear Mr. Hennessy teaching the same stuff, and he's like 3 sentences behind me. So I know we're pacing okay. All right, when you push something, that's the action force.
Mr. Wiley?
Yeah, what's up?
I have a question. What happens when an unstoppable force meets an immovable object? What'll happen?
Well, you can apply a force and still not move that object, but I feel like that's a line from something.
Yeah, Batman, like it's like a Joker scene,
So it's Batman Joker?
Yeah, no, it was like the Dark Knight trilogy or something like that. It was from one of those film series.
See, I recognize it, but do you remember what the response was?
It was like I forgot the response, but I know the Joker said this is when like an unstoppable force meets an immovable object or something like that. I think he was referring to Batman as like the unstoppable force and him as like some sort of removable object. Maybe it was that.
You know what that means? We need to watch this movie as a class assignment. See, now we know what we're doing Friday. No, but it would be fun. All right, so what do I have? All right, when you push something, that's your action force. I should put force right here, force. So it's your action force. It always pushes back. It always. And that's your reaction force. All right, we said it always occurs in pairs. The two forces act on different objects, right? If my force is acting on the wall is acting on me. So the action and the reaction force act on different objects, obviously, because I'm attacking the wall, so the wall attacks me. But as soon as I stop acting on the wall is like, no, we're cool, we're friends, right? Let's see what else this says. Reaction force is in the opposite direction, but it's an equal magnitude, okay?
Mr. Watley,
Yeah, what's up?
could you explain the jumping scenario?
Yes,
Yeah.
absolutely. In order for me to jump upwards, what has to happen? If
Push
I'm,
off earth.
let's say, yeah, I've got to push down on the earth. Let's say I'm hanging by a string. Okay, there's a string in this room and I'm hanging by it. My feet are not on the ground. If I kick my legs down, I'm not going to go up, right? But if I'm on the ground and I'm able to push off of the ground, I'm applying a force to the ground, correct? If I'm applying a force to the ground is going to put a force on me because it's a reaction force. Let's say we're swimming. All right, I'm swimming in the water. I am pulling on the water, so therefore the water is pushing on me. Imagine that. All right.
So you're saying that when we're jumping, we're pushing on the ground, and so the earth is pushing us up, basically.
Yes.
Okay.
Yes.
Okay.
And if we don't try very hard, it won't push very hard either. So we don't go very high. But the harder we push down on the earth, so you got to think of this differently than you've ever thought of it before, I believe. When I go to jump, I'm not pushing myself up. I'm pushing the earth down. I'm basically kicking really hard onto the ground, right? So when I crunch down and my legs are all folded up and then I do what we call a jumping motion, really what I'm doing is I'm pushing the ground down. But the ground is saying, hey, you pushed on me, I'm going to push on you. And it pushes us up, and that's what makes us jump. According to physics, in our physics mind, us jumping is the earth pushing on us. So if we lay on the earth and we don't push on it, it ain't going to push on us. All right, forget about earthquakes, but it's not going to push on us. But if we stand up and we push really hard with our feet against the earth is going to push really hard on us, and that's going to cause us to go up. When we walk, we're basically taking our feet and we're pushing against the earth, and the earth is pushing us forward because we're pushing back on the earth. So this is your Newton's third law. It's a bizarre thing to wrap your mind around. But as soon as you do, you're like, okay, I get it. And that my best example is hitting a wall, because if I hit it soft, it doesn't hurt. The harder I hit it, the more it hurts, because the harder I hit it, it's hitting me hard in equal force, just in an opposite direction. I'm hitting this way, it's hitting back that way. Let's see how we're doing. We're doing fair on time. I'm going to look through these examples real quick and just kind of read through this like we did on the first one. We said it always occurs in pairs. The two forces act on different objects, like me hitting the wall hitting me. Reaction force is in the opposite direction as the action force. Obviously, my action went this way, the reaction came back at me. Reaction force, it's always an equal magnitude. So if I hit the wall with 10 newtons, it hits me back with 10 newtons. It's equal and opposite. All right, let's see. Actually, I've gone through these examples. When you walk, you push the ground backwards, the ground pushes you forwards. When you swim, you push the water backwards, water pushes you forwards. A rocket engine pushes gas out of the rear of the rocket, and then the gas pushes the rocket forward. Let's see, I have something that popped in the chat. It says, is there a possibility where something we talk about or learn about fall under more than one law? Oh yeah, these work together so much. Or is there only one law when we talk about an action? A lot of times when we're doing equations, it'll be centered around Newton's second law, but we can sort of pull in some math with the third law. And let's do that. So let's do an example that has kind of math that involves the second law and the third law, because that's what someone's asking in the chat. They're saying, is it going to be one or the other, or a combination? So let's do an example. I have one in my hand, so I'm going to write this. It says that Austin, so somebody named Austin has a mass equal to 40 kilograms. Okay, and he's going to push Elmer I didn't make up these names, so I mean, whatever. And Elmer has a mass equal to 60 kilograms, such that Elmer ends up accelerating at 2 meters per second. And we want to know what Austin's acceleration equals. Okay, so the question is saying they're pushing on each other, or Austin pushed on Elmer at least. Austin has 40 kilogram mass, Elmer 60. Elmer accelerates at a 2 meter per second acceleration, and we want to know what Austin is going to accelerate with. So if we break this apart, we can say that Elmer, his force, we know that the sum of forces, see, I told you my summation sign is going to get ugly. Summation of forces is equal to mass times acceleration. We know that the sum of forces for him is going to be 60 kilograms times 2 meters per second squared. Therefore, his sum of forces, I'm telling you my sums look terrible, equals 120. And we said forces are newtons, right? So once we multiply those, that becomes a newton. Elmer's force is his mass times his acceleration, 120 newtons. Okay, so let's look at Austin then. His sum of forces equals, what is his sum of forces going to be? Anybody tell me?
120.
120 newtons. Okay, almost perfect. And I am so proud of that answer. How can it be more perfect though? The force is negative, right? It's going to be opposite. It's going to be equal and opposite. So if we said that Elmer's force is 120, that means that Austin's force is negative 120. So negative 120 newtons. Very, very good. It's the same size, opposite direction. Okay, so if we wanted to rearrange this for Austin, we'd have the sum of forces is equal to mass times acceleration. And if we're solving for acceleration, we would divide both sides by m. They cancel on the right. So we would get the sum of forces divided by mass equals acceleration. We said the sum of force was negative 120. We said the mass was it 40? Yeah, 40 equals acceleration. That means Austin's acceleration would be -3. Yeah, -3 meters per second squared is Austin's acceleration. So one person walks up and pushes another, but they both move back. You know, not that we ever hardly have a fight in this school, but you may have seen a fight on TV where they walk up and somebody pushes, but the person pushing doesn't stand dead still. They push, they go back, and so does the person they're pushing. So because that contact was happening, a force was being applied, there was an equal and opposite force being applied back to them. Two things, object A, object B, Austin and Elmer. We were able to solve for that force because we knew his mass and his acceleration for Elmer. So Austin's force is negative 120, but due to the third law, he pushed him in opposite action. Yes, absolutely. Because we were able to solve for Elmer because we knew his mass and his acceleration. So we can multiply that because sum of forces is mass times acceleration. That means Elmer experienced 120 Newton force. That means Austin had to have experienced a negative 120 Newton force. Make sense? So if I go out there and shove on my car in the parking lot, me and the car are going to experience the same amount of force. Let's imagine the brake is off, you know, there's no other forces. If I shove on my car, I'm probably going to move back more than my car is going to be displaced because my car has a bigger mass.
Mr. Watley, can I clarify something?
Absolutely.
So you're saying that 120 newtons is the direction that Elmer's going? Like when he pushes, he goes back. But then since Austin is going in the opposite direction, he's going at negative 120 newtons?
Okay, you're close. 120 newtons is a force. It's not a distance or an acceleration. I'm saying Elmer experienced a positive, Elmer experienced a force of 120 coming this way, where Austin experienced a 120 going that way. And we said positive and negative are directional in physics. So I'm going to say this way is positive, this way is negative. And so Elmer experienced 120, Austin experienced 120. Now this wall could experience 120, doesn't mean it's going to move. Or if it moves, the movement is so tiny we can't perceive it. This wall is massive. It's connected to an entire building. This building is massive. If I shove on it, it may move, but it's going to be such a small move, it is not even able to be registered on anything that measures movement, right? The mass of me compared to the mass of this building, I would move a lot by shoving on the building and it shoving back on me compared to its movement because of its mass. So I'm not saying Elmer moved at all. I'm not saying, well, actually I'm saying Elmer moved because Elmer had an acceleration, right? But I'm not saying he moved by 120. The force that was pushed on him was 120. And the response of his 60 kilogram body was an acceleration in that same direction of 2 meters per second squared. So we've got to bring in this new topic in our mind of force. Force is not velocity. Force is not acceleration. Force is what's being applied to something that can create an acceleration. So that's what that's coming from. I bumped this and now the screen changed a little bit, but not by much. Okay. Let me stop this share for just a second and see. How are we doing this new information? And it takes a bit to digest. Okay. It does take a bit to digest. Sometimes it's helpful to look up other videos and look up other explanations. First day of any big topic, it takes a minute. I'll tell you in on level, we do 1 day of Newton's law, and then on Newton's first law, we do a different day for second law and a different day for third law. We don't give it to them all at once. For AP1, we want to give you all the information so that then we can spend our time actually using it and developing our skills with that. Okay. So what I'm going to do now is I'm going to switch to the packet that's in today's Canvas. We had, let's see if I have it where we can actually look at what today's Canvas looks like. No, I don't have it. Not where I can get to it quickly. All right, so at the end of today, let me see if I can just pan over to it. I'll share my screen so you don't just have to watch me stare at my screen. So Chrome, dashboard, let's do that, share this. All right, so we go into our class. We're gonna go into the coursework. Let me slide that over. Now we are in forces. So we're in unit 2. Don't go back to unit 1, that would be sad. Forces in motion, and scroll up. This is our first week. Today is the 16th, so we're in here. We're gonna scroll up. We did forces in motion ideas. That was what we started with. We went through the 3 laws. Now let's do kind of a cool down. It's sort of like a warm up, but towards the end of class, let's do this, and then I'll help you get started on the homework. So if we look at that, let me stop sharing and bring it up on Adobe.
Mr. Watley,
Yeah, what's up? Yes.
For the Canvas, it says that Unit 2 hasn't been unlocked yet.
Oh, let me fix that. I'm glad you said something. Unit 2 hasn't been unlocked. All right, so today looks unlocked. Let me back up one. Okay, are you listed under me and Hennessy? Because under my side, it says it's unlocked. Let me go back to just the our blueprint and publish it from there. Maybe that'll force it. Is it when you click on Unit 2 forces?
Yes, I can't. It's not letting me access it. It says unlock. It's not unlocked, so it's not letting me go to it.
Okay, let me do. I'm going to back up. I'm going to share my screen again. I'm going to get you to tell me exactly where it stops you. So can you get this far?
Yes, that's as far as I can go. And if I press Unit 2, it just says it hasn't been unlocked.
Okay. Click refresh. Just make sure it's not just pulling out sometime that it used to be locked.
Yeah, I still have the same message.
See the green up here at the top of my screen where it says published?
Mm-hmm.
That should unlock it for you. Are you listed under anybody else's physics in addition to my own? Because it could be that the other teacher hasn't unlocked it. So if we go back to dashboard, does it have my name next to the class?
Yes, it does.
All right, so we go into this. I don't know why. Is anybody else
I think
experiencing this?
locking is
Mine
different from
isn't doing that
publishing.
too.
Yeah, I'm getting the same problem.
Yeah,
I am
mine's
too.
locked.
It's the same problem. It says this page is part of the module unit 2 and hasn't been unlocked yet. It's under like a big header called unit 2.
I think maybe from there you might have to scroll down and unlock it, but
No,
I'm
this
not
is where it
able to
unlocks.
access
If I click unpublish, that's where you can't get to it. And then I click publish and then you can do it. And this is from our class, so I don't know. I might have to fix it. I'll have to ask somebody that's going to be able to do it. So
Oh,
I'm-
it says locked on the left side, right next
So
to
that just
publish.
means that lock means that any change that I put in the blueprint applies to the yearly. That means
Oh, okay.
basically there's one that we all work from, and then we all have our separate classes. Locked means that we all have to share it. We can't make individual changes.
Okay.
So locked is normal. I'll have to figure out what's going on with this. Let's just work within mine and figure it out. I'm not sure what's going on because from my perspective, it should be open. Let's just get through this stuff today and then we'll figure it out. Check back on this by the end of fourth period, and by then hopefully I'll have it figured out. If not, I don't know. Let's see. Let's do this. Okay, how about this? Apple in a plane. Sorry to not be able to resolve that in class because the normal fix isn't there. But let's just finish up forces for today. This is Apple in a plane. David's sitting in an airplane flying over the Atlantic Ocean. Plane's moving very fast at a constant speed. He puts an apple out of his bag and places it on the tray in front of him. Put an X next to the major forces acting on the apple. All right, so is there a force by the tray pushing up on the apple?
No.
Yes, the normal force. It's a contact force. Anytime you touch a surface, you get a perpendicular force called the normal force acting on it. So it's basically what you're sitting in the chair and you're not falling through your chair because that force is pushing up on your backside.
Wait, Mr. Watley, how
Yeah.
is it perpendicular if it's pushing the opposite direction?
All right, so right now I'm not talking about like Newton's third law. I'm just saying that this is a chair, right? Let's say that this is a chair. And if I set my calculator on it, the surface of the chair is like this, and the normal force is perpendicular, it's going up.
Got it.
Without that normal force, my calculator would just fall through the paper and go to the ground. Just like you in the chair. Why are you not falling through your chair, through the floor, through the ground, and finding this in the center of the earth pulling you with gravity? Because as soon as you come in contact with something, you have a normal force, and it's perpendicular to that surface. Now, what about my calculator now on the wall? Which direction is the normal force pointing?
It's
Down.
pointing down.
It's pointing towards me because it's perpendicular to the surface. The surface now is like this. Perpendicular would be towards me. The normal force in this case, because if I let go of this, it's going to fall, right? Because gravity. But if I put it on top of this notebook, the normal force keeps it from falling. It is in balance. The normal force is balancing the gravitational force. Therefore, the sum of forces is zero. Constant velocity. It's weird. It takes getting used to. This calculator has no acceleration right now because the forces are balanced. What forces are acting on this calculator? Gravity going down, normal force going up. Okay. What if this calculator, oh, actually I have something on a string. All right, my school ID, okay? My school ID, what forces are acting on this ID card?
Earth's gravity, and then also I think your normal force, right?
All right, so
Is it tension force?
yes, tension, because my ID is not on a surface, it's hanging from a string. So tension is pulling up at the same force, the same value as gravity going down. How do we know they're balanced?
Stays in the same
The card
place.
is stationary.
Yeah, it has a constant velocity. It could be moving. If I pull this, let's say, let's see, imagine an old well where you had a bucket, and you had to lower the bucket, and you had to pull the bucket back up, right? just imagination, okay? You're pulling on a rope. Now, that rope has tension. It's pulling the bucket full of water up. If you pull it up at a constant velocity, that just means that the tension on the rope is balanced with the gravity pulling down. It is moving upwards. It is in motion. But if it's in constant velocity, the force of me pulling up is equal to the force of gravity pulling down. If it speeds up as it goes up, that means I'm pulling with more force than gravity's pulling down. If I start to slow down some, that means the acceleration is in the downward direction. That means gravity's pulling with more force than I'm pulling up. This again takes a lot of practice. We're going to get that practice, but it's going to take a lot of practice to kind of get used to. So let's go through this one real quick because I want to make sure we can get deeper into the next assignment, knowing that you can't access it. So the tray is pushing up on the apple because it's a contact force called normal. You're going to use normal a lot. All right, force of gravity pulling down on the apple, absolutely, force of gravity. He's not in orbit, he's not in space. Now the rest of them do not exist, so let's just go through them, okay? I just want to speed up to make sure we can cover this stuff. Is air pushing down on the apple? No, air is all around the apple, so if it's pushing at all, it's pushing at the same intensity all the way around it, so it's not just pushing down on it. Is it pushing up on the apple? No, it's all around it, and it's not really pushing on it at all. Force up by the plane in the direction the plane is moving? No, the plane and the apple, they have the same relative motion. So the plane's not pushing on it. It is inside the plane, so it's part of that relative motion. Force by the apple holding it onto the tray. No, the apple is not reaching down and holding the tray. No forces are acting on the apple because it's at a rest. Well, we know gravity is acting on it, so we can't say that. No forces are acting on the apple because it's inside a fast-moving plane. Again, I don't care where it is. If it's near Earth, it still has gravity acting on it. Okay, that gets us at least through that part. We need to make sure that this is not something that we rest on. We need to make sure we study these three laws and get a good idea of them. I want to go into the work that was going to be assigned for homework and get started on it so we can kind of see what it looks like and get some good examples. Let's see. Let me scroll through and make sure. Okay, there's nothing new on the chat, so let's do that. We've got 30 minutes. I won't keep you too much more, but I do need to go through this a little bit. Let's see, application, here, there. Okay, so this is what it looks like. It's a couple of pages long, I think. Let me get this out. I actually worked it. 1, 2, it's 5 pages, but it's not bad. And it's kind of fun in my opinion, but I'm also weird because I like physics. So true or false? For the false answers, explain what is incorrect. Okay. An object with a force acting on it cannot be in equilibrium. An object with a force acting on it cannot be in equilibrium. All right, talk to me. If you have a force acting on something, can it be in equilibrium? What does equilibrium mean?
Not moving.
Equilibrium in this case means balanced.
Does it mean stationary?
Forces. Equilibrium just means balanced. Balanced forces. So an object with a force acting on it cannot be in equilibrium. That's just saying if there's a force acting on something, can it have balanced forces? This is false. Because right now, we are all at equilibrium. We have balanced forces. We have a force acting on us. We have gravity pulling us down. We have normal force pushing us up. Imagine, I'm guessing that we're sitting on some surface or standing on some surface. We're not hanging from a rope in the middle of a room, right? I'm guessing. I mean, some of us might be a little acrobatic more than others. But this is false because we could have balanced forces and still be at equilibrium. An object with a net force of 0 must be at rest.
False.
At rest. You said false, right?
Yeah.
Right, absolutely, this is false. Because a net force of 0 just means balanced forces. So what does this mean? It means that we would have a constant velocity. Now, that velocity could be 0, but it could be anything. Balanced forces means net force 0. Let me write that over here. Balanced forces equals net force of 0. Equilibrium, balanced forces, net force zero. All that means the same thing. Use them interchangeably. An object with only one force acting on it can be in equilibrium. An object with only one force acting on it can be in equilibrium. True or false? You got to talk.
True.
False.
False. If we have one force acting on something, that's not balanced. If I'm being pushed this way, the only way to be balanced is have an equal force pushing me the other way so that I'm balanced, right? So if I only have one force acting on it, that's not a balance. So here we would say false. And we would say equilibrium means balanced forces. And I'm just going to use EQ for equilibrium. So EQ, equilibrium, means balanced forces. Okay, I'm hoping this work is starting to bring together some of the stuff we've been talking about. I really do. So now, yes.
Could you please go over the second question?
Absolutely, don't mind at all. An object with a net force of zero must be at rest. A net force of zero, what it means to us is constant velocity. Doesn't mean that it must be at rest. It could be at rest. It could have a constant velocity of zero, but it could also have a constant velocity of anything. Net force of zero means no acceleration, no change of velocity, which means constant velocity. That does include being at rest, but that doesn't mean it must be rest. It could be anything that's constant.
So does equilibrium mean net force of zero?
Yes. Net force zero, equilibrium, constant velocity, all those things are working hand in hand.
Mr. Wiley,
Sorry, go ahead.
there was like a problem that we did last where like there was a person that was running on top of like a moving train, like in the other direction, like say like the person was moving like 6 meters per second like east, and then the train was moving like this way, like in the other opposite direction. Would that be like a example of a net force or net force of zero?
No, because when we're looking at forces, we're going to look at the person inside the train as we would look at the train itself and the person inside. We can say what forces are acting on the train. And then when we talk about the person, we're going to go inside the train, forget about anything going inside the train. We're going to say like the world now only exists inside the train, and we're going to look at forces of that person, because we'd say that the person's world only exists inside the train. And anything that happens to the train is external to the person. So there is a relative motion between the two, but the forces, we're going to look at forces on the person or forces on the train. But we wouldn't be saying, hey, there's a force against the train, therefore pushing on the train and pushing against the person are going to balance each other, because it's two separate entities, two separate free body diagrams, which gets into it with number 4. I think number 4 might help a little bit, because you've got to be able to draw the free body diagram. And when I draw it for the train, I don't draw it for the person. I don't draw a free body diagram inside of a free body diagram. We have to decide what are the forces acting on and only draw one diagram, initially at least. So we're going to draw a free body diagram with all forces for each scenario, write the applicable net force equation. Okay, so they've got, this is net force in the X, this is net force in the Y. Okay, so that's what it's showing. Summation of forces in the X, which would be the horizontal, summation of forces in the Y, which would be the vertical. Okay, a 10 kilogram crate is resting. All right, so let's go ahead and draw this free body diagram. A free body diagram is nothing more than a box. Now, I like to put the mass inside the box so that I don't lose it. So I'm going to write 10 kilograms. This helps keep everything together and understanding, okay? 10 kilogram crate is resting on a tabletop. What is the weight of the crate? What is the normal force acting on the crate? Okay, it gives us the answers, but let's work it out. Now, this is not a part of the free body diagram, but just for fun, I want to draw the table. Now, most of the time when we do this, no. Why am I doing it today? Because I want an example so that we can see and kind of understand what's going on. Let's see what color. I can't find that blue color because there's like a menu trying to hide it. What forces are acting? Are there any forces left and right on this box?
No.
Not at all. This crate has nothing pushing or pulling on it. So in the X direction, there's 0. Okay, summation of forces is 0. What about in the Y? What forces do we have?
Gravity.
Gravity. So I'm going to call this mg. You can call it FG, but FG or mg, I just get used to doing mg. And then whatever, any other force we have on this box, crate?
Normal.
No.
Normal. Which way does normal go?
Up.
Up. Force normal. Okay. Now, the magnitudes or the size of the arrows you draw indicate the size of the force. So if you have a big force, make a big arrow. If you have a smaller force, make sure it's relatively smaller than the other ones. So when you draw these for a test or a quiz or any kind of assessment in the AP test, make sure that your arrows, if one force is twice as big as the others, it should be twice as long. Okay. Now, what is the force of gravity for this object if we calculated it?
9.8. Because the answer is 98.
Now, so the mass is 10, right? And we were saying the acceleration of gravity is 10. So mg, that's mass times gravity. So what's 10 times 10?
It's 100, but on the question it says that the answer is 98.
I know, quit looking at the answers. That's because they use 9.8. Stop looking at the answers. All right, so we know mass times gravity. This is going to be 10 times 10 equals 100, right? The force normal. How do we know what the force normal is?
Wait, Mr. Wiley, how did you know like the normal force was in the up direction?
Because the box is sitting on the table and the force normal is always perpendicular to the surface that it's in contact with.
Perpendicular, okay.
So it's resting on the bottom. The bottom of the box is sitting on the table, so that means the table is pushing up on the box. Normal force is always a perpendicular force at 90 degrees to how it's in contact with it.
I have a question.
Yeah, what's up?
How'd you know the mass was 10?
The box tells me, the question tells me. It says a 10 kilogram crate is resting on a tabletop.
Oh.
It's okay. It's totally, we're hitting you with a lot of stuff today, so it's easy to get lost. Now, I want to ask students, what is the force normal on this box? Number.
Negative 100.
Don't worry about direction right now, just the magnitude.
100.
Why did you say 100?
Because it should be the same as weight.
You're right,
Yeah.
but how do you know? I want everybody else to understand why you understand.
Box is resting.
Yeah, is the box moving? So could we say it has a constant velocity? Right, the velocity is 0 and it's not changing. So the crate has a constant velocity, right? So does that mean it has balanced forces? So that means the downward force balances the upward force. And there's only one upward force and only one downward force. So they must balance each other. So the upward force is equal to 100 newtons and the downward force is equal to 100 newtons. So then the sum of forces would be 100 newtons minus 100 newtons, and that also equals 0. This box, it's not moving, therefore it has a constant velocity. That means all of the forces are balanced. There are no horizontal forces. There are 2 vertical forces that balance each other. Now, for like 1 out of 10 students, this is very easy. For 9 out of 10, it's going to take some work and some practice and some questions. All right, let's look into number 1. Yeah, what's up?
So I understand the concept of this, but I'm getting confused as to your previous example. When you hit the wall, why is it the same output for when you hit the wall? Because in this
You cut off. I didn't get the end of your question.
Sorry. So when the box is at rest, there's a balance of forces. But when you hit hit the wall, why is there also the same output for your input, I guess, for how you hit
Why
it?
is there an equal and opposite action reaction?
Mm-hmm.
Okay, it happens here as well. Now, when we're talking about the balance of forces for this crate, this is not Newton's third law, because Newton's third law says that if the earth is pulling down on the box is pulling up on the earth, right? If the tabletop is pushing up on the box must be pushing down on the tabletop. So Newton's third law just means that for every pair, there's an equal and opposite force. So when I hit the wall, I hit it with a positive 20 newtons. So it hits me back with a negative 20 newtons, just meaning this way's positive, that makes this way negative. And I was using the wall example so that I could prove to you that it was always an equal force, because if I hit the wall soft, it hits me soft. If I hit it hard, it's going to hit me hard. And that's why it hurts when I hit it, because it's hitting me back hard. If I walk up and shove a student in the hallway, if I shove a little student, he's going to fall down and I'm going to move back a little bit. But if I shove one of our linemen from our night football team, he's going to move a little bit because he's got a big mass. But when I shove him, I'm going to fall back even further because by comparison, I have a smaller mass. I'll have more acceleration. He has a bigger mass, less acceleration. So Newton's third law plays in a little bit, but we can't try to force Newton's third law into everything that we do. We have to understand, okay, what forces are interacting with this object, not what forces this object is exerting, but what forces are being exerted onto the object. So that's where we kind of reserve Newton's third law for a second and say, okay, yes, I know this object is also exerting forces, but let's just talk about what's being exerted on the object itself. Does that make sense?
Sorry.
Go ahead, go with the next question.
Mr. Watley, I wanted to know, so you have two like Newton forces present here
Yes.
in like the free body diagram. Why isn't one of them negative since they're acting against each other?
All right, so think of it this way. Positive and negative just dictate direction, correct?
Yes.
Okay, so now if you look at just my picture, don't I have an arrow pointing up next to force normal?
Right.
So I've
So-
dictated direction, haven't I? I don't have to say positive, negative if I say up and down, don't I?
Right. So
Okay.
the arrows are basically replacing the negative or positive sign in a way.
Correct. Now, when I go to the summation of forces box there, you see how I subtracted them there? I did a
Yes.
subtraction here because I'm saying they're going in opposite directions. I have 100 going down, I have 100 going up. They're in opposite directions, so I subtract them.
Right.
But when we look at the free body diagram, I have an arrow going up and an arrow going down. That is establishing the direction, so I don't need positive or negative. So this comes back to, does gravity always have to be negative? It's like, no, gravity just has to have an arrow going down. That's all. See how my mg has an arrow going down? I say it's down at 100 newtons. That's all I need. Because
Would it
that's,
be wrong? Sorry, go ahead.
no, ask me.
Okay. Would it be wrong to have a downward arrow and write negative 100 newtons?
It may make it confusing because what if the overall force is downward, okay? And you call it negative 100 newtons. And then I say the upward force based on tension is 60, okay? And I would tell you, you need to take 100 and subtract 60 from it. But what if you put in your calculator negative 100 minus 60? You would get negative 160, when what you really need is 40 downward.
All right, I see you.
So that's where it gets dangerous. And that's why I like the flexibility of saying, hey, you don't have to call gravity negative, because in forces, we're not going to. We're going to say it's downward. We're not going to say it's negative. We're going to establish which direction and give it a magnitude. All right, let's look at number 5 and see if it helps a little bit, get a little bit more information. This was the minimum stopping point for today, was to get through number 5. And let's just see where we are with things. So Billy has a 3-kilogram notebook. So I'm going to draw a free body diagram, which is just a box. I'm going to put the mass in the middle so I don't lose it. 3 kilograms. He sets the notebook on a table. Now, I'm not going to draw the table this time. The first time was just so we would see it, but it's not normal to do. He sets a notebook on a table and presses downward with a force of 5 newtons to close the notebook. What is the weight of the notebook? What's the normal force acting on the notebook? Okay, this is a good question. This is a challenging question. It's not easy like the first one. All right. Let's start with what are some forces we know that are acting on this? So talk to me.
Gravity.
Okay, so I'm going to call that mg. What else do we have?
And the force Billy's applying.
Okay, so we'll call that force applied. Is that okay?
Yeah.
Okay, what else do we have?
Normal force.
Normal. Okay, now they told us the force applied is 5 newtons. That's correct, right? Okay, so I'm going to go ahead and put that in my diagram. 5 newtons. All right, can we calculate the force of gravity for this notebook? What is it?
10 meters.
That's the acceleration. What's the force of
30.
gravity?
30.
30, right? Mass times acceleration, 3 times 10. So that's 30. Okay, now force normal. What do we think the force normal is in this case?
35.
Why?
Because you have to add all the forces that are going in the same direction.
How do you know that you're just going to add them all together?
Um,
Is the notebook moving? Or is it resting on the table?
it's constant.
Right.
So
The notebook is, even though he's pushing down on it, the velocity of that notebook is 0. It is not moving through the table. It's not falling to the floor. So our forces are going to be balanced. Okay. So if the downward force altogether adds up to be 35, what does the upward force need to add up to be?
35.
35. Exactly right. So that means this has to be 35. These become like puzzles. Believe me, they become like puzzles. So in the horizontal, we had nothing. In the vertical, we had, we can do it either way. We can say 35 minus 30 minus 35. We can say, it doesn't matter which one you subtract from the other since they're balanced, but we can say that it's, let's do 30 plus 5 minus 35 equals 0. Now, I didn't put the newtons in just because my writing in the dialog box, but ideally you would have 30 newtons plus 5 newtons minus 35 newtons equals 0. Because the book, even though he's pushing on it, it's not accelerating, it's not moving, the velocity is 0, so we know the forces are balanced. There's only one force going up, the force normal. There's 2 forces going down, Billy pushing down and the earth pulling down. You can also see that my arrows, I didn't do a great job in doing it, but let's say if I were to do this a little bit better, the push down maybe would have been a little bit more like that. A little bit of push down force, a lot more force from mg.
I have a question.
Yes, what's up?
Is the force, is it always gonna be like after subtracting, is it always gonna be 0?
No, we will have some acceleration.
Okay.
But when you have something that you know is not accelerating, you know you can balance it. We're starting with balanced forces. Okay, they're going to start calling classes out, so we're going to be finished up for the day. Hopefully by the end of the day, you'll have access to this. If not, email me and I will send you the Google link to this. Let me see if I can actually put that in the chat. Let's see. I'm going to stop the share. I'm going to put in the chat the Google link to the work that we're doing right now. So that way you can copy and paste this and you can work on this even though you don't have access to, for whatever reason. All right, that is the link. It's in the chat right now. You're able to get to the homework, work on this. If you get stuck, communicate with me. I want a good start to this unit because this is really a fun one, but you gotta get your bearings first, okay? Get those bearings, do the work, ask the questions, and we're gonna have a good time. Watch for your grades too. By midnight, your grades will be in. And if you're struggling, start communicating and making some decisions too, because for Friday, starting on Fridays, when we have to decide if this is the right place for us, okay? You guys are awesome. Let me know if you have any questions, concerns. Once you get that link, you can bail, but you need to work on this entire packet between now and next class.
Mr. Watley,
Yeah, what's up?
So for number 5, for the force of gravity, you said it was 30. So would we use the 3 kilograms of the box times the 10 of the normal force of gravity to make it
Yes.
30?
The force of gravity is the same as the weight, and it's always mass times 10.
Okay.
Mass times 10 is always the force of gravity.
I also had another question for like number 5. I saw like the answer part, and I get the 34.4 Newton part, but the first part says 29.4 newtons. How do you get 29.4 out of this?
One second, I'm looking at this. Oh, okay, I'm looking at this. This one, the answers aren't always right, and they're not right on this one.
Oh, okay.
It's absolutely not right. When they answered for the normal force, I'm sorry, what is the weight? The weight is 30. They have,
Okay. Yeah.
wait, no, they're right. I'm sorry. I was looking at the answers in reverse. What is the weight of the notebook? The weight is 30. They said it's 29.4 because they're using 9.8. Okay. Then they said, what is the normal force? And it says 34.4. And we said 35. They're using
Okay.
9.8. We're using 10. Their answers are right.
Okay, so the normal force is 35 because of the FA and the force of gravity acting upon it, so that would be 35.
Correct.
And then the weight would be 29.4 because of the gravity, right? And the
Right. So what it's saying is since this book is not in motion, that means the forces are balanced. We were able to calculate or be told all the forces down, and we know that has to balance the force up if we have a constant velocity.
Okay, thank you, Mr.
So
Watley.
total force down was 35, so total force up has to be 35.
All right, thank you.
Mr. Watley,
Yeah, what's up?
how can weight be a Newton?
Because it's Newton is a measurement of force, so is pounds. So is pounds. But when we get on a scale, we see pounds. There are scales that say Newtons. So when you weigh yourself on a scale, you're weighing yourself in pounds. That is a measurement of force. And you're not measuring your mass. You're measuring the force of gravity. Because if you took that same scale to the moon, it would say something different, right? So your scale just you're used to a measurement of force for your weight in pounds. And in physics, we use Newtons. That's the difference.
So weight is basically how much gravity is acting upon you.
How much mass you have times the acceleration of gravity of the planet you're on.
All right, got it. Thank you.
No problem.